Hi, welcome to another edition of Linear Algebra. Today we are going to continue our conversation about the applications of dot product and the concept of projection. So we have seen quite a few examples of this so far. We are going to take a look at three more examples along the lines we have already done. One would be projection of a vector on a plane. Another one would be reflection of a vector in a plane. And finally, we are going to take a look at projection of a point on a line. Let's go ahead and see what these problems look like. So here are the three problems. Let's start with the first one. So first one, as the picture here implies, we have a plane, we have a vector u, this red vector. We want to find the projection of that on the plane. Perhaps we call it projection P. So the idea is that we just drop a perpendicular from points of the vector on the plane, and that's our projection. We want to figure out what that projection is going to be. Closely related to this thing is a reflection of a vector in a plane. Well, you have seen some computer generated movies in which computer is drawing some picture for you. One of the simplest thing that you might come across there is getting the reflection of something in a plane. The plane is acting like the role of a mirror, and we want to have the projection there. So here we have the vector u, and the plane acts like a mirror. Projection of it is going to be u prime. We are going to see this problem is closely related to that one. Third problem we are going to look at is projection of a point on a line. This is particularly for a line whose parametric equation is given. So we have a line, we have a plane, we want to drop a perpendicular directly from the point to the line. We perhaps look for two things. One is what's the location of this point. Let me just give some names. Suppose the point that we have here is point Q, and then we drop a projection here. Let's call it H. We want to know where H is, and we want to know what this distance is. Let's call that little h. So these are our objectives for today. Again, this is going to show us nice applications of dot product and the concept of projection. So this is in continuation of many other examples we have done. A long list of them are here, and we have three more. Okay, first one, projection of a vector on a plane. Let me so item number one, projection of a vector on a plane. Very simple. Let's just redraw this picture again. Suppose we put the vector to rest against our plane, so that's going to be easy for us to think about it. So this is the vector u. We are dropping a perpendicular from this end, so this is perpendicular to our plane. Beginning of a vector, we have moved it on the plane itself, so the projection is going to be this. Let's call this one vector P. So how can I get the vector P? Well, very simple. Get the normal vector to the plane. So this is something that's easy for us to get. And normal vector to the plane, let's call it n. Then find the projection of u on n. So we drop perpendicular here, and with that projection given to us, let's call this thing little n. So n, vector n, is going to be projection of u on n. So our original vector was vector u, and then we said let n to be normal to the plane. So n is a projection of u on n, so we have simple formula for that. It was u dotted with n divided by n dotted with n times n. That's a formula for this vector n. Let me color it this way. So this is vector n. Well, how can I get vector p? Notice that n plus p is the vector u. If I take the vector n, add p to it, I get u. So I can easily get p as u minus n. So the projection vector that we want, p, that is the projection of u on the plane. The plane has normal. N is equal to u itself minus n, which is this, u dotted with n over n, n, n. That's it. That's the formula for the projection. So several problems in your textbook relates to this. Let's do one of them. So for example, problem 48 from section 1.3. There it goes like this. Suppose it says find projection of u given as 1, 0, minus 2 on the plane. Okay, the planes in the book are typically denoted with a script letter, like something like that, plane P, given with the equation 3x minus y plus z equals to 0. As soon as we have the equation of the plane, we know what's the normal to that plane. Is that right? Do you remember how to find that? So you want to think for a second. What was our simple way of extracting equation of a normal? Well, simply the coefficients. So 3 minus 1, 1. So the projection, or P, we called it P here, is equal to the original vector that you have, 1, 0, minus 2, minus, now take a dot of these two, so it's going to be 1, 0, minus 2 dotted with 3 minus 1, 1. Dot of this thing with itself, it's just its norm squared times, don't forget you have to multiply with this thing, so this shows up 4 times. We said they don't cancel out or anything. So 1, 0, minus 2 minus numerator 3. 1 times 3 is 3. 0 times minus 1 is 0. Minus 2 times 1 is minus 2. Adding them all up. So 1 times 3. 0 times minus 1. Minus 2 times 1. And then multiplying these two and adding them up is 3 squared minus 1 squared and 1 squared. And then you have that vector again, 3 minus 1, 1. So we write a little bit, 1, 0, minus 2. Numerator is obviously 3 minus 2 is just 1. Denominator 9, 1, 1, that's 11. And then you have, of course, then 3 minus 1, 1. You do a bit of arithmetic here. So 1 minus, this is 311, 0 plus 111, and that's going to be what? Minus 2 minus 1/11. Is that right? So the projection turns out to be, let's clean this up. So 11 minus 3 is 8/11, and then 1/11, and then 22, and that becomes minus 23/11. So when you enter on WebAssign, these are what you are entering there. You don't convert to decimal or anything. When you are working for yourself, it's easier to take these kind of vectors and factor denominator out, but when you enter, there's no place for you to enter this. Perhaps you just enter the numbers exactly this way. So that's it. We found the projection of a vector on a plane. Now problem number 2. So we had 3 problems to do. Reflection of a vector on a plane. This is a good place for you to try your hand at this game you're playing. All sorts of little ideas related to projection. So the idea here now is you have a plane again. For this plane, you know what the normal of it is from its equation. You have some vector u. What do you want to do? So again, the idea is that you try to do this thing yourself. What is the reflection? How do you get that? What's the physical meaning of reflection? You want to convert that idea to a simple mathematical recipe. So again, this is the cue for you to find that straight path and then come up with a formula by yourself instead of just listening to me. So you do that, and then you come back and verify. If you don't know where to start or what to do at certain stages, just get a little bit of a clue. Again, go back to the drawing board, try to do it yourself, and do iteration over and over again until one of these problems you do it from beginning to end all by yourself. Now, first time it could take quite a bit of time. You might have to struggle. Maybe it takes half a day for something that I explain here in just 2 minutes. That's okay. You just take your time, do it, and gradually you build your confidence in this, and then you can do just what I'm doing. So the idea here is we are taking reflection. How do you get a reflection? Okay, let's go back to a very simple description of what reflection is. So if you have a point and this is a mirror, by reflection we mean, well, you go straight to the mirror, go equal distance to the other side. This is where the reflection is going to be. So if this is a point A, its reflection in the mirror, equidistant from that mirror, is where the A prime is going to be. That's of course for a mirror that's standing still. If the mirror is moving, we have an interesting situation which we are not going to talk about here, but if you're interested, you can let me know. Okay, so here's a still mirror. Reflection in that mirror is that point. So here, if I have this vector, I come straight to the mirror or the plane. Let's call this thing H, and then keep going. Equal distance to the other side, and then we have our reflection. Let's draw the reflection in blue, maybe. Oh well, I went a little bit too deep maybe, so I have to change this one perhaps. So suppose this is the where it hits the mirror. let's go ahead and call this reflection perhaps u prime. So the question is, if I have the vector u, just like what I had here, and I have my plane, the way you have the plane is by its normal, how do I find the reflection in that mirror? What do you think we should do? Okay, so this is I've given plenty of the clues right now. You should be ready to do this thing yourself. So we said okay, so let me emphasize, let's try to nudge you to actually do this thing yourself. That's the only way you really learn. So try to figure out formula for u prime. Okay, here, how did we get to p? So I'll take u, subtract n from it, come down from u to p. Well, if I subtract one more time, I come to u prime. If you want to go to the other side, subtracting n brings you here. Subtract n one more time, it brings you to the reflection. So u prime is going to be u minus 2n. So that was all there was to it. So if this is the let's call this thing vector little n, if I take u and subtract n, I've come to h. If subtract another n, I come to u prime. That's my formula for u prime. So u prime is going to be u minus twice who was n. N was this was the little n. This is our little n. So that was it. 2 u dot n over n dot n times another n. So if we have let's use the same numbers of the last problem. 1 0 minus 2, and n was coming from our equation for the plane, minus 3x minus y plus z equals to 0. And so n from there was 3 minus 1 1. You go ahead and calculate u prime here, just like what we did last time, except that you have a factor of 2 in this case. So you're going to have 1 0 minus 2 minus twice this was our u was 1 0 minus 2 dotted with 3 minus 1 1, denominator 3 minus 1 1, this is a 1, excuse me, 3 minus 1 1, and then one more of 3 minus 1 1. So you go ahead and calculate this thing, and I guess what we get is going to be 5/11, and then 2/11, and then minus 24/11. Okay, so that was simple. Now later on in the semester we can take this formula and motivate idea of matrix out of it. So this whole thing can be written as a matrix times the vector u. So one motivation for matrix could be expression like this. This would be the second example of motivation for matrices. The first one we saw was at the intersection of two planes, and now we have this thing which gives us a pathway to matrices. Okay, item number 3. So let me emphasize this is so the problem was U prime is reflection of U in a plane with normal n. Item number 3 we promised we are going to do was projection of a point on a line. The method we are going to use here is something that the textbook had also recommended for some of the other problems we had done before. So so you want to pay attention to this, and if you want to use it in other problems, of course it's available for you. Now, projection of a point on a line, one version of it we have done. If you have the general equation of a line in 2D and then you want to find the projection of a point on it, distance or the projection, we have done this problem already. When it comes to a line in 3D, the situation is going to be different than what we had for a line in 2D or a point and a plane in 3D. Think about it, see why is it that we need to do this differently than the other problems. But here is the approach that the textbook recommends, and we are going to practice it in the context of this problem. So we are in 3 dimension usually, and there is a line here. The line is specified by some starting point, and you remember as before that we had equation of a line given to us as or a location on the line is some starting location that is given plus there is a so-called direction vector in play, v or d or something. So there is a direction vector. You keep taking steps along the v to arrive at any point that you like, for example r. So this is equation of line in this type of problems, equation of a line in 3D. Now what we have is some point out here, let's call it Q. What we are after is, if I go straight to this line, meaning shortest distance to this line, first of all, where do we arrive at? Let's call that point H. Find me this location H. Next, tell me how far should I go to get here? So that would be the distance little h. So we want to find Q is given. Q in a space is given. We want to find two things. Find H, which is closest point on the line to the point Q, and find little h, distance of Q from the line. These two things we want to find. Well, again, the reason we need a different approach here, I want you to think about it. Why is it that we are not using the idea of a normal vector n and so on? How come that doesn't work easily? What should we do? So here is our approach. From equation of a line, you have some point on the line. This one is just r0 itself. Take this r0 and connect it to the point Q. Okay, so we have vector r0q. Well, if I take r0q and find the projection of it on v, I'll get r0 to h. So R0H, vector R0H is projection of R0Q on V, which by now I'm sure you can write it even in your sleep. How can we find a projection of some vector on another vector? What was the formula? Again, let me nudge you to write this to participate and hopefully finish the problem yourself. So that's a cue for you to tell me what's the projection of this blue on this red. Well, R0Q, take R0Q, dot it with V, divided by V squared, V dot V, multiplied by V, that's it. That's the projection. So if I have the vector R0H, how do I arrive at the location H itself? If I want to go to H, first of all, travel to R0 first, and then go as much as R0H. So R0H, let's write it, start from R0 and add this thing to it, R0Q dotted with V over V dotted with V times V. So that's a recipe for finding H itself. Okay, so extract your R0, Q is given, difference of these two is R0Q, and then you do this and you're all done. Well, how do I find the length of this distance from Q to H? Well, we are going to use the Pythagorean theorem. We are going to say H squared is R0Q squared minus R0H squared. Is that right? Here we have a right triangle. Is that right? Here's a right triangle. We just use the Pythagorean theorem on it, and that's going to give us the answer. So hypotenuse is R0. Find that squared. How do you do that? Well, distance formula. R0H. We have that. And then I have to find the length of it. You find the length of this vector, square them, subtract, and H squared is going to be equal to that. Let's go ahead and do an example of this problem. Again, this is one of the homeworks in this section, 28, section 1.3. It says, suppose Q is given to us as 0, 1, 0. Line, typically shown by script L, is given in that format, parametric format, as x, y, z is equal to 1, 1, 1 plus t times minus 2, 0, 3. So who is this? This is our R. This is our R0, and this is our direction vector V. So item number 1, how do we find this location H? I need to find the R0Q, and when I put it here I get my H. So R0Q. How do we find vectors whose beginning and end are given? Just take the last point minus starting point, and that is the vector. So Q is 0, 1, 0, starting point is 1, 1, 1, and when we subtract it I have minus 1, 0, minus 1. H was R0 plus R0Q V, 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 V. So R0 is our starting point, 1, 1, 1. R0Q is this vector, minus 1, 0, minus 1. Sorry. V is the direction vector of the line, minus 2, 0, 3. over minus 203 minus 203, and then for good measure one more round. So if we calculate whatever this thing is, the location of h is going to be given 111 plus, I have 2, let's write, and then minus 2, 0 times 0, minus 1 times 3, denominator is minus 2 squared, 0 squared, 3 squared, then one more round, minus 203, and then we get 111, and what is this, 2 and minus 3, so it's minus 1 over, that's going to be 4 and 9, so I have 1 plus 2, 13, this is just 1 and 0, and 1 minus 3, 13. So this becomes 15, 13, 1, and this one looks like 10, 13. This is the location of h. And then for the distance, you find the length of r0q, that's the hypotenuse. R0h, you have to calculate. R0h is just this portion. R0h, this is so we want to find the length of that and the length of R0q, so square them, subtract, and so I'm going to leave that to you to find out what the distance is. Okay, so we have seen many examples of the dot product, applications of dot product in finding the projections. We have looked at this problem in many different ways. Some of the questions in this section are based on what we have done. I'm going to leave some of them to you, for example, finding distance of parallel lines, parallel planes, and so on. There was one question that I left to you as a mini challenge of, let's remind you, if you have two lines in a space, they could intersect, they could be parallel, or they could be what they call skew, that is, they do not intersect and they are not parallel either. How do you find the distance of those lines? So try to think about that. If you are interested, let me know. We are going to move on to applications of vectors. Some of the very basic applications are going to be brought up here, and then after that we are going to go into higher level stuff. We are actually going to start with what is usually considered to be beginning of linear algebra. So what we have done so far, all of this stuff is motivation for starting linear algebra. Some of your classmates in other sections might start with matrices at the very beginning of their linear algebra class. That's one style of diving into this topic, but I believe that is a very abstract looking approach to get started at that level. Hopefully what we have done with points and lines and planes and the dot products and projections and such, it has prepared your mind for what we are going to do next. So we started with geometry. We went through things that you have seen in high school, but we did it by using linear algebra. In the next chapter we are going to go up one level higher up, and we are going to introduce you to matrices. Before doing that, we are going to have a little bit of introduction, application problems, applications of vectors to physics. We are going to take a look at forces, how to resolve forces, and how to add the forces, and so on. So that's going to be short application 1.4, and after that we are going to have our new chapter. Chapter 2 is going to start at that point. Okay, until next lecture, good luck and God bless.